Welcome, everyone. For today's prep, we're going to introduce the idea for series. So in this set of notes, we're going to look at the limit definition for series using partial sums. So we're going to see what partial sums are. We'll look at some algebraic properties of convergent series. And really what we're going to be looking at is how do we write out the first few terms for a sequence of partial sums. So let's start by looking at, well, essentially what we're going to be considering. So a series, and sometimes we call this an infinite series. So what an infinite series is we have an infinite sequence. So we have some sequence, we have some list of terms, a sub n. So, and essentially what we do with a series is we take that list and essentially we try to add all the terms together in the order of our list. So let's remember, we have our original sequence. So our original sequence is just a list. A1, comma A2, comma A3, comma A4, and dots. It keeps on going. And we use the curly brackets to indicate that we're talking about a sequence. So this is really just a list. So we just have a list of terms in a specific order. And what we're going to try to do with a series is essentially take all the terms in our list here and add them together in that same order. And the way we're going to denote this is, so the way we denote the original sequence is with our curly brackets, but what we're going to use to denote the series, the infinite sum essentially, is with big sigma. So this sigma. So you want to think of this sigma here as really just a fancy addition symbol. And usually we want to specify the starting index value. So we're going to go from n equals 1 to infinity. But when the starting index isn't necessarily too important, sometimes we might just leave that off and write, sigma an. So this is the notation we're going to be using for a series. And essentially you want to think of it as we're trying to add up all the terms in an infinite list. And, well, as we're going to see, whenever infinity gets involved, you can't always do it. So we're going to see that this cannot always be done. If you have a list of terms, an infinite list, you can't always add them all together. Sometimes you can, though. So if the sum exists, we're going to call the series, we're going to say that it's convergent. And if the sum does not exist, we're going to say that the series diverges. Okay. So how are we going to do this? How do we add infinitely many terms together? So our regular addition symbol, our regular addition operation here, is only for adding a finite number of things. And so our usual strategy for dealing with infinity is, well, convert it into a limit problem. So the idea for how to actually add an infinitely many terms together is, well, we're not. We're going to add up a finite number of terms. And that we can do with just regular addition, so there's no question there. We're going to add up a finite number of terms. And then the idea is we're going to see what happens to that finite sum as we use more and more terms. So we're going to compute the limit as the number of terms we're adding together approaches infinity. And this first step, adding a finite number of terms, this takes us to our first topic here, which is partial sums. So ultimately the goal is to see what happens when we add essentially all the terms in our infinite sequence together. Well, we can't really do that. So what we're going to do is we're going to add up a finite number of terms. And this result is called a partial sum. And we're going to call these partial sums S sub n. So S sub n is going to denote the nth partial sum. So essentially what this is normally for a series, we're going from n equals 1, and we want to add it all together. So we go from n equals 1 to infinity. Well, for a partial sum, we'll call our index I here. So we're going to go from I equals 1, and then we're not going to go all the way to infinity. We're going to stop at some number n. So we actually stop. So this is actually a finite sum. So we take our first term of our sequence A1, we add in our second term A2, and then A3 we add that in as well, and we keep going. We keep adding terms in until we get to that nth term, and then we actually stop. So this is a finite sum. Okay. So by doing this over and over, we get something called the sequence of partial sums. So we have our original sequence A sub n. So this is the list of the terms that we're trying to add all together. And by forming partial sums here, we get this new sequence, which we'll call S sub n. And what this sequence of partial sums is, the first term of this brand new sequence that we get is just the very first term of our original sequence. The second term of this sequence of partial sums is where we take the first two terms of our original sequence and we add them together. S3 is the sum of the first three terms. S4, the sum of the first four terms. And we keep doing this. So let's get a little practice calculating these partial sums. So we have a series here, an infinite series. And here we've just explicitly written it out. So we have 1/3 plus 1/9 plus 1/27 plus 1 over 81. And it keeps going. The general term here is 1 over 3 raised to the power n. And essentially, we're trying to add all these terms together. So what we want to do is we want to write out the first four terms of our sequence of partial sums. So S sub 1, the very first term, what is this? Well, it's just the very first term of our original sequence. So in this case, it's 1/3. Well, what's S2? The second term of our sequence of partial sums. Well, it's the sum of our first two terms. So 1/3 plus 1 over 9. What's S3? Well, we take the first three terms and we add them together. So it's 1/3 plus 1 over 9 plus 1 over 27. And, well, one more, S4. What's S4? Well, you can probably guess it. We take the first four terms, add them together. And that's it. So, when we're talking about series and the sequence of partial sums, we're going to be talking, there's kind of two sequences involved. So it's important to kind of keep track of them. So let's just go back up. So we have our original sequence. So this is curly bracket A sub n. And if we write out the terms, this is just the list of the terms. A1, A2, A3, A4, and so on. So that's one sequence we're going to be considering. But then we also have our sequence of partial sums. So this is a brand new sequence that we're forming. So we'll call this one S sub n. And if we were to write out the first few terms for this, the very first term would be A1, so just the first term of our original sequence. But then the second term of this brand new sequence would be A1 plus A2. And then the third term would be A1 plus A2 plus A3, and then so on. So it's going to be important to kind of keep track. When we're talking about series and sequences and partial sums, we have the original sequence. This is the original list that we're trying to add all the terms together. And what we're going to be doing is we're going to be forming a brand new sequence of partial sums where we're just adding up a finite number of terms from this original list. And so that's what we did in example 1. So example 1 here, let me get out of the way. Our original sequence. What's our original sequence? Well, it's curly bracket 1 over 3 sub n, where n is going from 1 to infinity. And if we were to write out the first few terms for this original sequence, it would just be 1/3, comma 1 over 9, comma 1 over 27, maybe get one more in there, 1 over 81, and then dots, and then we end our curly bracket. So that's the original sequence. What we're doing with this sequence of partial sums is we're getting a brand new sequence. So in this case, the first term of this new sequence is 1/3. Then the second term is 1/3 plus 1 over 9. And then the third term is 1 over 3rd plus 1 over 9 plus 1 over 27, and so on. And this is kind of this is going to illustrate finding this general formula. So we had this nice little formula here for our original sequence for the kind of the nth term. This is the difficult thing with the sequence of partial sums. Getting the general formula here is usually pretty difficult. So for right now, we're just writing out the first few terms for the sequence of partial sums. Let's try one more. So we got the series. Now we're using sigma notation here. So we're looking at the sum from n equals 1 to infinity of 1 over n. So when we look at this, the starting index value here is n equals 1. So let's just write out the first few terms for the original sequence. So this is going to be 1 over n, and we're going to start our index at n equals 1 and go to infinity. So the original sequence here. And let's write out the first few terms. So when we plug n equals 1 in, we get 1. When we plug n equals 2 in, we get 1/2. And then n equals 3, we get 1/3. And then 1/4. And then 1/5. And so on. So I've just written out the first 5 terms here for this original sequence. Now, what we're going to do with the sequence of partial sums is essentially we're going to try to add up more and more of these terms from this list. So now let's write out the first few terms for our sequence of partial sums. So what is S1? So the very first term. Well, it's just the very first term of our list. So S1 is going to be 1. What about S2? Well, S2 is when we add the first 2 terms. So it's going to be 1 plus 1/2. Well, what about S3? Well, add up the first 3 terms. And then S4, add up the first 4 terms. S5, add up the first 5 terms. So S4 would be these 4 terms just added together in that same order. And then S5 is going to be these 5 terms added together. So as we kind of go further and further in this new sequence of partial sums, we're basically just kind of taking the previous results and we're adding the very next term from our original list. So when we go from S3 to S4, we're taking our value from S3 and then we're just adding in the very next term from our list. And so what we do here is essentially this is giving us a brand new sequence. So the first term is 1. The second term is 1 plus 1/2. The third term is 1 plus 1/2 plus 1/3, and so on. So I've written them out here, but we could also indicate that as a sequence here. So what we're doing is, with a sequence of partial sums, we're taking some original sequence and we're progressively adding more and more of the terms together. And what we'll see in class is we'll see, well, when does this new sequence actually converge? And when does it diverge? And that tells us something about the infinite sum. All right, so we'll save that for class. So we'll see you then. Bye-bye.